is on.
All right. Good morning, ladies and gentlemen. Today we're talking about the conservation of energy, or sorry, conservation of momentum. We'll get to the conservation of energy. Today's just a conservation of momentum. So we mentioned in the email that conservation laws are around us. So we use them in a lot of different places. Here we're going to be talking about conservation of momentum, but conservation of energy we'll also take a look at. In chemistry, we use conservation of atoms when we're balancing chemical equations. In Chem 12, we'll use conservation of charge, taking a look at electrochemistry, and so on. So here we're talking about when momentum is conserved, we're talking about the momentum before an event, and sometimes I refer that as a bang, because a lot of times that event is a collision of some sort. So things colliding together or things exploding outward. And so what we will do is that we'll talk about the momentum before. And so we'd use P before because momentum is, symbol for momentum is P, mass times velocity. And so then that equals the momentum after. So momentum is mass times velocity. But if we have objects that are colliding together and so on, then we have to indicate that we're keeping them separate. So we might talk about M1, V1, and we might have a second object, so that'd be M2, V2. We might even have a third object, M3, V3, and in fact, we could have any number of objects. And in this system, in this collision, we're going to take a look at the sums of all of those momentums, and that has to be equal to the sums of the momentums afterwards. So you can think about, like playing pool. You shoot the pool ball and it hits the rack of balls, and balls go bouncing off in different directions. So there's our M1, M2, M3, and so on. Well, likewise, afterwards, we're going to have momentum. Now, so we'll have, the momentum of the first ball, the momentum of the second, and the momentum of the third, and however many there are. But M1, V1 looks like M1, V1. So what we do is that we indicate that there is a change. And, like if you're playing pool, the mass of the pool balls don't change. The balls all, they stay the same. But what does change is the velocity. And so what we do is we put a little mark by the velocity to say, hey, this is a new velocity. And we call that prime. So we'll say, often with two objects, we would say M1, V1 plus M2, V2 is equal to M1, V1 prime plus M2, V2 prime. And that's how we talk about it, how we distinguish the different objects and what's changed. Now, this is an example where the masses haven't done anything, and we'll get, or they've remained separate, and we'll get to other examples. So first of all, let's take a look at a video. Hopefully this will work, and pull this up here, and we're just going to watch a short clip. Now, this object here, device, is called a Newton's cradle, and we're going to have to see what happens. I mean, you've seen my pool balls that I have, my 10-pin, my 5-pin, some pool balls. My bowling balls, I have the 10-pin, 5-pin, actually have some pool balls as well. And the whole reason for getting those was to create a Newton's cradle with this. And as we get back into the school, I'll have to see about actually, I think, making those, because time is running out. Anyways, let's take a look at this. Let's take a look and watch. So if you think about it, what we have is we have the ball coming in, and it hits the next balls behind it, and then the last one goes flying out. Well, how many collisions are there? Well, every time, so this comes down, there's one collision, but it runs into this one 2, it runs into this one 3, runs into this one 4, and then it moves out. And so what we have is a transfer of momentum through all of these balls through here. And that's sort of the amazing part of this, what makes these things cool. And you can see that it continues going back and forth because this one goes out and then it swings back and hits the other way. And so we get this transfer of momentum going back and forth. Now, if this was perfect, then in essence, this could keep on going forever. But we can notice things. There's no gap. Here, there's some other gaps. In the initial images, we could see that they were not lined up perfectly. I'm thinking, why did you spend all this time putting this together, not have it perfect? Anyways, and you'll notice that these balls in the middle, they begin moving, and that's because the collisions are not perfect. And so we're losing energy, we're losing momentum just because things weren't lined up properly. Anyways, let's watch a bit more. Bouncing back and forth, and you get more and more movement happening. That's kind of cool. So now they're bringing 2. And so we're getting this momentum being transferred. All right. So that's an example of a collision that's happening and the conservation of momentum, where the mass times the velocity of the first object gets transferred through to the last object. So we're going to talk about 3 types of interactions, 3 types of collisions that we can have: elastic, inelastic collisions, and inelastic explosions. Yes, it is as exciting as it is. For an elastic collision, we're going to have m1v1 plus m2v2 is equal to our m1v1 prime plus our m2v2 prime. Now, we are dealing with just 2-dimensional collisions, 2-dimensional, 1-dimensional collisions. So you can think of this as railway cars on a track. There is no room for them to not collide and so on. That's where we are in Physics 11. Physics 12, then we start taking a look at pool balls as they go running off, and you hit another one, and then they go off at various directions. This is grade 12. This is grade 11. All right. So these are an elastic collision. They bounce off. Now, elastic collisions really are very rare. Subatomic particles will have truly elastic collisions. Generally, our collisions are someplace in between a perfectly elastic and a perfectly inelastic. But for some collisions, bouncy ball and something like that, we'll generally say, hey, that approximates an elastic collision well enough. In an inelastic collision, the way the equation changes, but it doesn't change. What we am doing is just rewriting part of it. If we have an inelastic collision, then what we have is that M1 sticks together with M2. They're now joined together. Now, if they're joined together, then the velocity V1 prime has to equal V2 prime. And we can then, if V1 prime and V2 prime are the same, we can just factor out that velocity and just have it at the end. So let's just call it V prime. So this is an inelastic collision. 2 independent objects come together and then they stick. 2 railway cars. An inelastic explosion is just the opposite of this. And you can think of an inelastic explosion, say, as a bullet in a gun. So you have the mass of the gun and the mass of the bullet, and they are tied together. They are moving together with the same velocity. And then afterwards, we have the mass of the bullet and the velocity of the bullet, and the mass of the gun and the velocity of the gun. They're now independent. Now, these in some ways look like 3 different equations. Really, these are 2 alternate forms of just this equation up here. But sometimes it helps just to see these things. And again, you're allowed a cheat sheet to have any of this information. All right. So let's first begin with elastic collisions, and let's go through an example from pool. A pool ball is shot at 1.2 meters per second at a second pool ball. If they collide head-on, what happens? Well, seemingly there's some information missing. So let's talk about m1 v1 plus m2 v2. The second has a velocity that's equal to 0. That's one thing I forgot. So m1 v1 prime plus m2 v2 prime. All right, what do we know about pool balls? Do we know the mass of a pool ball? In this case, we know that the mass of a pool ball will equal the mass of another pool ball. I mean, that's the whole purpose in pool, that the balls have all the same mass. So m1 will equal m2, which will equal m1 and m2 over on this side, which means that we could actually rewrite this as mv1 plus mv2 is equal to mv1 prime plus mv2 prime. And then we could, factor the m out. So we have mv1 plus v2 is equal to mv1 prime plus v2 prime. But then we can see that if we factor that out, what we can also do is divide both sides by m. And then what we have is v1 plus v2 is equal to v1 prime plus v2 prime. Now, I went through a lot of work here just to point out that we're not told what the mass is. And in this case, it doesn't, because the masses are all the same, it doesn't matter what the mass is. We can just take a look at what the velocities are. All right, so what we know is that we have our first ball has a velocity of 1.2 and the second one has a velocity of 0. So we could put 1.2 meters per second plus 0 is equal to our v1 prime plus our v2 prime. And I say, what happens? Well, the sum on this side has to equal 1.2 meters per second. And on this side, the sum of these two have to equal 1.2 meters per second. Now, they are colliding head on. And if you've ever played pool, you know that if you get things lined up correctly, you shoot one ball in and the next ball goes bouncing out at the same velocity and the other one stops, in which case we would have v1 prime is equal to 0. And so then v2 prime has to equal our 1.2. Now, v2 prime is equal to 1.2 meters per second. The first stops. So you sometimes see that in pool. The other option is, well, what if you miss? So like this is still 1.2 meters per second. That's all of the velocity we have on the left-hand side. And if they miss, well, that means our v2, the second ball isn't going to start. So we have just v1 prime plus 0 is equal to 1.2. And in this case, the ball misses. And it continues on with its same velocity, which goes back to our idea of inertia. An object in motion remains in motion, traveling in a straight line, unless a force acts upon it. All right, so we've got, go away, there we go. So we have a simple case where, such as two pool balls colliding on, and this is really a special case where we have this idea that the velocity for one becomes 0 and the next one takes all of that velocity and goes on. We'll take a look at some other examples, I think, as we go on, that are a bit more generalized. Well, here's a bit more generalized. Here, a 3-kilogram ball is moving at 1 meter per second, and a 0.2 kilogram ball is moving at negative 1 meter per second. The 3-kilogram ball then moves with a velocity of 0.3 meters per second. How fast is the 0.2 kilogram ball moving? All right, so sort of the idea is that we have this object and this object, and they're moving past each other. So the idea of the negative sign, again, is that negative signs tell us direction. And so the negative tells us that it's moving the opposite direction. Then we have a bang. And we know that our large ball continues on with a smaller velocity, and then we have our smaller ball, and that's what we don't know. So these two are moving towards each other, and what sort of motion do we have afterwards? So you can see that in essence, what we're doing is we're saying this direction is going to be positive. All right, so we'll have m1v1 plus m2v2. That's equal to our m1v1 prime plus our m2v2 prime. Our m1, well, it's 3 kilograms, and it's moving at 1 meter per second. And then we have our 0.2 kilograms, and it's traveling at -1 meter per second. And then after the fact, we know we have our 3 kilograms times 0.3 meters per second, and that's equal, and that is added onto it, our 0.2 kilograms, and we have our V2 prime. So what we're doing is we're looking for this V2 prime. All right, so 3 times 1 is equal to 3. 0.2 times -1 is -0.2. That's equal to 3 times 0.3, so that'd be 0.9, and plus 0.2 V2 prime. Right, so we're going to move this over to the other side. It's connected by addition here, so we're going to use subtraction. So minus 0.9, we'll go minus 0.9 on this side. All right, so we have 3. Oh, where's my Casio FX260 solar? There it is. Yes, I could do this in my head, but or on paper or on screen. Anyways, we have 3 minus 0.2 minus 0.9. So that's equal to a 1.9 on this side. And so this is canceled out, and so that's equal to 0.2 V2 prime. So we're going to take our 1.9 and divide that by 0.2, and our V2 prime then comes out to be 9.5 meters per second. How does that compare? 1, -1, 0.3, 9.5. This is like 9.5 times faster than what it was traveling with to begin. Does this really happen? Does this? Come on, sir, don't lie to us. Does this really happen? And the idea is yes, it happens. We're gonna take a look at a video, and in the video, what they do is they take a basketball and they have a tennis ball on top of it. And what they do is they drop it. And so we have the ball. Now, we know from kinematics and so on that everything accelerates due to gravity at 9.8 meters per second squared. And so if these are both motionless, both have an initial velocity equal to 0, the final velocity is going to be the same for both of them because they're both being accelerated by the same acceleration. And so you're going to get both of these falling at the same rate. But then what happens is that the basketball hits the ground. It hits the ground first. And when it hits the ground, then it bounces off and bounces back up. And so when it hits the ground and bounces up, its velocity is upwards, but the tennis ball still has a velocity downwards. And this is the point of contact or the collision that we're going to be taking a look at, or that we were taking a look at in this last question. So we have this ball going up, and this is where I said this is 1 meter per second. We have this ball coming down at 1 meter per second, but it's the opposite direction, so that's why we say it's a negative. We're saying upwards happens to be positive. So this happens very, very quickly. So we'll just go back. We're talking about this ball here colliding with this ball, and this one continues moving in that same direction. What happens to this one? And we said, hey, it's going to be moving at 9.5 meters per second. Big change. And all we're doing is saying this is how we would set this up. Now, I do this at school. Would take you down to the gym and we'd take a basketball, and sometimes we use a baseball. It gets a little bit dangerous. Well, let's take a look. I've got another video queued up here, and by Physics Girl. Let's see how this goes.
Check out how high these different balls bounce. The basketball, the super bouncy ball, and the golf ball. Now I'm going to try the golf ball on top of the bouncy ball on top of the basketball. And then I'm going to explain how it's related to a supernova.
So,
did you see that?
way up there.
Probably not. So here it is again. The golf ball bounced to 28 feet. We dropped it from about 3.5 feet, so it went up 800% of its dropped height. In fact, if you consider that by itself, the golf ball bounces about 70% of its dropped height. It went as high as if it had fallen from 40 feet up. That is awesome. So how can we get the golf ball to bounce up with that much energy? Higher. Where does it get the extra energy? As the basket.
Okay, so they're talking about energy here to begin with. And there is conservation of energy. There is energy that comes into this, and we have a transfer of energy between the basketball to the golf ball and so on. But they then go on to focus on to the momentum, and that's where we're at in terms of the momentum. So let's take a look.
Basketball bounces, it compresses, storing elastic potential energy. As it releases, it springboards the tennis ball upward just at the right moment. This is like the double bounce on a trampoline when you jump right before someone else. You prepare the elastic of the trampoline by stretching it and storing energy, which can then bounce the jumper even higher. In the same way, the basketball stores energy in its compression and is able to push the tennis ball. But just like the double bounce preparer, the basketball can't go as high. You can see that here. It bounces even less when 3 balls are dropped together. Also, during that transfer of energy, some momentum transfers from the basketball to the tennis ball. And since the basketball starts with way more momentum because of its larger mass, the tennis ball's velocity.
Okay, just get that. The basketball has larger momentum because it has a larger mass. The basketball and the tennis ball are moving at the same velocity. The velocities are the same, but the momentum of the basketball is larger because it has a larger mass. Objects that are out there moving at the same rate do not have the same momentum because momentum is the product of the mass and the velocity. So in this case, the object, the basketball with the larger mass, is colliding with the tennis ball. The larger mass, the basketball is moving upwards while the tennis ball in essence is moving downwards, and we get that transfer of momentum that sends the tennis ball way up into the air.
Because of its larger mass, the tennis ball's velocity increases by a lot, and it flies up, up, and away. Now back to the triple super ball bounce. Now you get the energy from the basketball's bounce being transferred into the bounce of the super bouncy ball, which is then transferred to the golf ball's bounce. You put the same.
The interesting thing to know, I'm going to back this up, but if you watch closely, you actually see the deformation that is happening in the basketball, this ball, not so much this ball, but you can see that they actually squash and indent into it. And that's part of what elasticity is about, is that you have this non-permanent deformation. You know, think back to class. I've got that gray ball that's filled with sand. It does not bounce very well. It has an inelastic, permanently deformed situation. Let's take a look. So there you can see it's flattened there and it's flattened there.
From the basketball's bounce being transferred into the bounce of the super bouncy ball, which is then transferred to the golf ball's bounce. You put the same amount of energy or momentum from 2 more massive objects into a smaller object, and it will go much faster. Epic! Just like the explosions of a supernova, which may seem unrelated, but what we just did is analogous to the process that occurs during the explosion of a supernova. Just like our more massive basketball transfers momentum to the smaller balls, energy from the dense core of the supernova is transferred in a shock wave that moves through the star to the less dense layers and accelerates them outward at a super high velocity. More massive or denser layers in the core of the supernova begin to collapse when fusion stops there. The collapse is halted when the neutrons in the core actually touch, sort of. This causes the implosion to rebound and bounce outward. You end up with a dense core left behind and these wild outer shells of star exploding outward. Pretty cool. And of course, if you try this at home, which you should, you have to make sure the balls are perfectly vertically aligned because any off-centeredness gets amplified by the 2 points of contact, which is why we sadly couldn't get the quadruple tower of balls to work. But if you put a little ring of hot glue or something similar on the balls, it helps to balance them. Happy physicsing!
Happy physicsing? Huh. Oh well. She's physics girl and I'm not. All right, so let's go on. Oh, we watched the video, done that. All right, here we have an inelastic collision. A 6,000 rail kilogram rail car is traveling at 2 meters per second, collides and sticks to a 3,000 kilogram rail car moving at -3 meters per second. What happens? All right, so let's just draw these things out because you know I like drawing things. We have this rail car, this is 6,000, and it's traveling this way. And we've got our 3,000 kilogram rail car, and it's traveling along in this direction. Bang! They connect together, and so let's go bang. Then we have our two rail cars, and they're connected together. We want to know what's going to be, in essence, happening over here. All right, so again, we set this up. M1V1 plus M2V2 is equal to, there's our equal sign, which is our bang. And then with these things are connected together, so we can talk about M1 plus M2 times the velocity. All we've done is factor out the velocity from these two things because the velocity has to be equal to the same. All right, so let's substitute in our values. These are not complicated calculations. There we go, complicated calculations. But it just, matter of putting the numbers into the right place. Make sure that we are taking care with our negative signs, and we should be good. So what we're doing is saying this direction is positive. So we'll have our 6,000 times our 2 meters per second, and then we'll have our 3,000 times our -3 meters per second because it's traveling the opposite direction. And then we're going to have our 6,000 plus our 2,000, 3,000. Yes, Haley, I said it wrong, but I corrected myself. Times our velocity. I don't know, Haley. I'm picking on you for today. So here we have 12,000 kilogram meters per second plus a -9,000 kilogram meters per second, and that's equal to 9,000 kilograms times our velocity. So this would be equal to 3,000 over on this side, and we're going to divide both sides by this 9,000 velocity, and that's equal to 0.33 meters per second. So what does that mean? That means that these two cars are moving off in this direction. How do we know it's that direction? Because it's a positive value at 0.33 meters per second. Traveling towards each other. This one's traveling faster. This one has more mass. Bang. They're now stuck together, and they continue rolling in this direction. That's what we mean by what happens. And the signs tell us the direction and so on. All right, here we have a 0.2 kilogram golf ball shot at 80 meters per second. That's pretty fast. And sticks into a 10 kilogram stationary watermelon. I think this would be cool to do. How many times would you have to do it before you actually hit the watermelon? How far is the watermelon going to be? Who is going to get hurt? All right, so we've got our golf ball that's traveling at our watermelon. Bang. Now, would it really be a bang, or would it be sort of like a whoosh? And then we've got our watermelon with our golf ball, and they're moving off together. Here, velocity is equal to 0. Right, so we have our M1V1 plus our M2V2 is equal to our M1 plus our M2 times the velocity. This is what happens. All right, so we have 0.20 kilograms times our 80 meters per second, plus we have our 10 kilograms times, well, how fast is the watermelon moving? It's stationary. Does that mean it's made out of paper? Wrong, stationary. So this is 0 meters per second. I don't know. It's a Thursday morning and I'm here. All right, so then we have our 10 plus our 0.2, doesn't matter how which direction we add these things, times the velocity. Now, the 0.2 of the golf ball is small compared to this, but we'll still include it. So 0.2 times 80 is equal to 16. This is equal to 0. So over on this side, we have 16, and this is 10.2 times our velocity. So we go 16 then divided by our 10.2, and that's equal to 1.6. Now it's a positive 1.6 meters per second, which means that it's moving towards the right. Now, if you think about it, the watermelon's not moving to begin with. There's really no way that as a combined unit, they could be moving towards the left. What you would have to have happen is the watermelon would somewhat elastic, so the watermelon would move towards the right, and then the golf ball would move back towards the left. But that would be an elastic collision, not an inelastic collision. So there we go. Combined mass, they move towards the right. All right. Here we have another inelastic collision, but this case is an explosion. And so what we have in that case, we have our M1 and our M2, and they have because they're combined together, they have their own velocity, and then they break apart and they move off. So M1 V1 prime and M2 V2 prime, they move off independently of each other. So here we have a 4,000 kilogram rail car stuck to a 10,000 kilogram rail car. I don't know where they get these rail cars from. My budget never allowed me to do this, nor to have a spring large enough to do that. Okay, so here we have our 4,000, and here we have our 6,000 kilogram rail car. The spring between them pushes them apart. And what we find is that the 6,000 kilogram rail car is now traveling at 2.4 meters per second. And so then we know that our 4,000 is probably going to be moving in this direction, right? We need a direction that's positive, so let's make this direction to be positive. Let's set up our equation. So we have our M1 V1, no, let's change that, sorry. So we have our M1 plus our M2 times our V, and that's equal to our M1 V1 prime plus our M2 V2 prime. Well, M1 plus M2, so that's our 4,000 plus our 6,000 times our velocity. Well, the idea behind this is that they're not moving. So our velocity is equal to 0. And so then we're going to have our 4,000 V1 prime plus, then we have our 6,000 and times our 2.4. Okay. Extend this page. So 4,000 plus 6,000 is 10,000 times 0 is equal to 0. A lot of times you're going to see that one side will be equal to 0. And that just means that the momentums here have to add up to 0. So let's bring, well, and that's equal to 4,000 V1 prime. So we have 6,000 times 2.4, that's equal to 14400. This is going to go over to the other side. So we're going to have negative 4,000 V1 prime, and that's equal to 14400. So our V1 prime, we're going to divide this by 4,000, or negative 4,000. And that comes out to be negative 3.6 meters per second. So what we have the spring between. This one moves off at 2.4. This one is going to be moving off at 3.6 meters per second in the negative direction. So it's going towards the left. That's what that negative sign is telling us. Does that make sense? Light rail car, heavy rail car. Momentum has to be conserved. So what we have is we have the momentum in this direction, and we have the momentum in this direction. And this momentum plus this momentum have to equal 0. Because up here, no velocity. We have mass, no velocity. Momentum is equal to 0. After the fact, the sum of the momentum still has to be equal to 0. So here we have a positive, here we have a negative value, and these are going to be equal to each other. Momentums are equal to each other, not the masses, not the velocities. Large mass, small velocity. Small mass, higher velocity. Same momentum. Positive momentum, negative momentum. All right, I think we're coming up to the end. All right, a 50 gram bullet is in a 7 kilogram gun. The bullet leaves at 600 meters per second. What is the motion of the gun? So, I don't know, I like drawing guns. Oh, can't draw a barrel very well. All right, so here we have, all right. It really used to be that even a high school physics lab would have a gun. At least I think so. And you would, do experiments with them. All right, so what we have a bullet in there, and then we pull the trigger, and then the bullet goes shooting out of the gun. All right, so we have m1 plus m2 times our velocity is equal to m1 v1 prime plus our m2 v2 prime. Well, we are assuming that the gun is stationary on our lab bench, which all stands to reason and would be the case, in which case this velocity is going to be 0. And so if the bullet is going this direction, what direction is the gun going to be going? Well, the gun should be going in that direction. So let's go through. So 50 gram bullet, so that's 0.050 kilograms plus 7.0 kilograms times our velocity, which is 0, is equal to 0.050 kilograms. And it's traveling at 600 meters per second. And then we have our 7 kilograms, and v2 prime is what we're looking for. So this is equal to 0.05 times our 600. So that would be equal to 30. Right, so this is going to come over as a negative 30 onto the left-hand side. Negative 30 is equal to 7v2 prime. Divide both sides by 7. And we get v2 prime then is equal to a negative 4.3 meters per second. So the gun is moving that direction while the bullet goes off in that direction. That's your kickback. And to work against the kickback, you put the stock of the gun against your shoulder so that your body, you don't have any velocity happening. You don't have that kinetic energy happening between the gun and your shoulder. It's all joined into there, and that in essence effectively increases the mass of the gun because that you're holding your body against it, and so you have increased mass, and so the velocity is going to be that much smaller. But sometimes you'll see in movies they'll show somebody taking a very small person holding onto a big gun, and they pull the trigger and they go flying backwards, and it's because of the kickback. Sometimes you see, like particularly World War II movies where they've got cannon set up, and they shoot the cannon, and the cannon moves backwards while the cannonball moves off forward direction. Or even old Master and Commander on the far side of the world, watching their cannons shoot. The cannons move backwards. They're tied off with ropes to keep them going far too far because the cannonball is going the opposite direction, going outwards. All right. So here I have some review questions for you to do. This is an important topic. Sometimes it takes people a little bit of time to I feel, to catch on to this. So I'm going to give an additional worksheet out on Monday. So this will be Thursday, Friday for this. If you have questions, please contact me. I don't mind going over these more in detail. But we're talking about conservation of momentum. M1v1 plus M2v2 is equal to M1v1 prime plus M2v2 prime, the general format that we would use to see this. We modify this. This is standard. This doesn't change. In fact, but we modify this if they're colliding together, M1 v1 plus M2 v2 is equal to M1 plus M2 times v. So this is, they're sticking together. Or we have M1 plus M2 times v is equal to M1 v1 prime plus M2 v2 prime. Here, this is the explosion. Three forms, sort of, just one equation, really. All right, I've been talking far, far too long. Hopefully this goes well. Try these questions, see how they go. And I hope you have a great day. All right, take care. And I need to do this. Come over here, and we are going to stop live streaming.